offshoots of the exact formalism towards the search of an exchange correlation energy density functional, the functional derivative of which is the Kohn-Sham exchange correlation potential. So the second one is an R dependent function, and the first one is a functional derivative of a functional. So that's the connection, and in that sense it is very unique. It's a unique representation of potential. So LDA, local density approximation. So this all of us know, it is nothing new, but put in a perspective which had a foundation which was mathematically exact. HK theorem 1 and 2 and Kohn-Sham formalism. So with that, Thomas Fermi did not have that particular luck. You know, they had to just start with some kind of, assume that it is like free electron, and kinetic energy is also free electron, and everything is free electron. You know, that's where it was not very very successful. But one must say that the Thomas Fermi model is exact when nuclear charge becomes very large. It is an exact DFT at Z going to infinity. That is point number one to note. And second point is that, you know, there is something very interesting history about this. If you read the literature, there was a very well-known famous person, physicist, Edward Teller, who is in Manhattan problem and all that, but he was doing a lot of initial work in many other areas. One of the areas which fascinated him was also Thomas Fermi model. And in the Thomas Fermi model, what he proved in 1962, remember the date, in 1962, Teller, that same Edward Teller, is known as a Teller's theorem. And the theorem states that no molecule is stable within the Thomas Fermi model. It's a Teller's theorem. Thomas Fermi model started becoming like, no. No molecule is stable. Okay. So it's called Teller's theorem. Molecules do not add to become more stable than their individual atoms in the Thomas Fermi model. Right. So it's called Teller's theorem, 1962. And it's commendable that in 1964, Cohen gave this Hohenberg-Kohn theorem 1 and 2. It's very interesting. Right. So it revived everything back to the density-based approach. Okay, so with that said, let's start with, this is where we left. This is unknown. It is a functional derivative of the unknown exchange correlation potential. Exact until this point, that becomes approximate the way you want to cook up, using your intuition or luck or collaborative efforts and so on, the exchange correlation energy functional and its functional derivative. Okay, so next lecture was here. Now, let me begin with John Purdue's quote. Again, the spirit here is that, you know, it's the same effort, whether you do wave functional method or density functional method or anything else for tomorrow. You want to understand the electronic structure of an electron system in general, not just in ground state, but any state. Okay, so that's your ultimate. Computationally, you want to compute. So it so happens that since we have the experience of the wave functional theories, that you have to depend upon some approximation, right? Helium, you can't solve exactly. You can solve near exact. You can stretch the limit to 60 decimal places out, but it is not exact. It doesn't stop there. Okay, it's not like hydrogen atom minus 0.5 atomic units. Okay, ground state. So, however, the correlated wave function theory, which is the post-Hartree-Fock theory, right? So, Hartree-Fock model is the orbital picture, and then you have the post-Hartree-Fock models, and there are a large number of them, and the most famous one is where our couple cluster expert is sitting here. So the gold standard of the wave functional theory. But again, it scales so highly with respect to the number of basis set that you can't do more than a few atoms together at that level of accuracy. Anyway, but chemists want to do, nobody can stop chemists. You know, when Popper gave that ZDO, everybody started doing CNDO, INDO, NDDO for All systems where ZDO may not even stand good. Okay, but then they want to do, why not go to bigger molecule and so on, because molecules are there, properties are there, let's see whether it works or not. So correlated wave function theory, Purdue says, it gives right answer because you have Hartree-Fock space, which is for the exchange only thing and a single determinant thing, you have the exact exchange only model. The correlation model has to be built upon it. It is important, though small in percentage, it is important because long range interaction, when two atoms or two molecules come together, it is the tail portion that interacts. Okay, so therefore, though small, the initiation of bonding, the switch is there in the correlation, right? That's the important point. Now, the density functional theory, and this is Purdue's amicable language, which I will read. Almost, it gives density functional theory almost gives the right answer for almost the right reason at almost the right price for almost all systems of interest. Okay, so he has not left anything for any criticism, but point to note here is that these two things are the same arms of the same effort of human minds to grow their knowledge in an advanced state as time proceeds. That's the main thing. So one has to learn from each other and proceed. And hopefully the machines will do, although you will always require the guidance from human beings. Right. Now, here is what happens since the 1965 paper of Kohn-Sham. All kinds of approximations. This N here is the physicist notation of density rho. Okay, density rho, irrespective of any spin, the probability that any electron with any spin will be found, irrespective of wherever any other n-1 electrons are with any spin, is rho. Okay, and that is an experimental quantity. It's an experimental quantity, right? You can measure it by X-ray diffraction method. So then what happens there is the main thing is here Hartree world. Hartree world is where there is no non-classical interaction. Every interaction in the Hartree model is a product wave function. It is not even antisymmetric. Okay, it's a product wave function. It doesn't satisfy the permutation of two electrons which are identical. Okay, and the exchange gives you a minus sign. So that property is not there in the Hartree wave function, right? So that is there, but that is there for the base. This is not so in the wave functional theory. In wave functional theory, the base is Hartree-Fock model, where Fermi correlation is included. The like spin exchange interaction that corrects for the extra rho and rho coulomb that has been taken in the J rho is corrected for by the self interaction when I is equal to J. Okay. Now, this is the first LDA that was given in 1965 paper by Kohn-Sham, right? And what they did was simply for both exchange correlation, use the electron gas models. It so happens that, as Manoj told in the morning, that exchange part for homogeneous electron gas at R. Okay. In general, it's a different system. You have homogeneous electron gas, exchange energy, and to be more precise, the exchange energy density per electron, which he actually wrote down. Exchange energy per electron, so that the total exchange energy will be integral of per electron exchange density multiplied by the density, and you integrate it out. So that is how the recipe was actually put forward. So this is how we will compute. Okay, so that was it, and that part, as you know, EXC has both exchange and correlation. In addition to that, it has also the TC. Right? And therefore, not only the ground level of the ladder of successive improvisation of the electron correlation effect is different. Hartree-Fock in wave functional, Hartree in the density functional, right? You also have the differences that I'll come to that a little later on, but let me just, because of why people started doing, in spite of all these approximations, Why they wanted to do that? And of course, as is well known, that if the n is the basis set size, then the scaling of the computational effort goes always as n to the power 3 for DFT, mostly, if it is the local energy density functional. Non-local ones, for example, hybrid functionals and all that, where you add some non-local part, it becomes N4 and so on, because Hartree-Fock scales as N4. So N4 is the Hartree-Fock. So you see, while the wave functional post-Hartree-Fock methods depend upon Hartree-Fock model as a base, which itself goes as n to the power 4 because of the non-local character of the exchange potential, you have here N3, which is going with the local potential, local density, rho of R, right, to begin with. And the simplest model that you can imagine is rho of R and local. How? Obviously, Thomas Fermi has told us long time back. Okay, for this piece, only for this piece, exchange correlation energy density, assume that in the space of a molecule which is quite unlike the metal, right, which is a very system which is localized, assume that at any given point R, in the smallest possible imaginable volume area d tau, the density is known as rho of R. At that point in that volume space, small volume, the 3 electron homogeneous gas expression for exchange part is valid, and also for correlation part valid. The thing is that exchange part for homogeneous electron gas is exactly known, but correlation part is not known. Okay, that has to be simulated. Right? That has to be simulated. Again, from the knowledge of very good computations that existed at that time. I will talk about it briefly a little later. Now, the point that I'm making here is that, because of this kind of scaling, all right, this kind of scaling. So imagine that if you go beyond LDA and also beyond the GGA, which depends upon, in addition to the density at a point, it also depends upon the derivative of the density in the immediate neighborhood of that point R, in the smallest possible imaginable space in the molecular density distribution, you have always N3 dependence, and therefore the success of GGA kind or meta GGA was quite good, because you could do big molecules, and for where you could not have any value for reasonably accurate properties. Okay, now later on the story changed, because the ladder tells you that here you beyond this, here until this point you have local, semi-local, but here it becomes non-local. Okay, because you start working with Hartree-Fock for hybrid and so on, so that will be covered up, and then of course you have range separated potentials, because Hartree-Fock exchange part is not good enough. It doesn't go as -1 by R at large R. You have to have -1 by R. So you do the range separated potential. There is a talk in this particular course, which I'm sure you will enjoy. And then there are many others ideas. So the important thing is that this is very good. We have to learn from MP2 onwards and so on. And they have also been very helpful in giving us the starting point. All right. So, for example, you use the basis that has been developed to give very good post-Hartree-Fock result. So, you use extensive enlarged polarized diffuse basis set to replace the Kohn-Sham orbitals. Okay. So, that's very important point to note, and one must know this. Now, so Pratim, this is a slide. So, correlation part in the wave functional theory is written as the non-relativistic exact Hartree-Fock result of energy and the difference with the Hartree-Fock energy. This is the Hartree-Fock is the base in the wave function theory. In exchange correlation part, it is exchange density functional, correlation density functional, and kinetic correlation density. Right? It's very different. Right? Although for ground state, this is not very large. It's small quantity as we know today. Manoj is not here. He has been one of the early workers in this field. Anyway, so this is the difference. All right, so when we talk about correlation, but one has to be very careful because the equations will tell you what is the final result, but you have to work them out. Okay, so this is the important difference between the correlation treatment. But that yeah, yeah, so that is the reason. Yes, right. Yeah. The homogeneity is not there. The PAR has done a lot of work on the homogeneous properties of this RG PAR, where both of us spend a lot of time. Yeah. But yeah. Now okay, so let me come back to it little later, because that has been now, if there is a problem, you have to find out, is there any use of that situation? So people have been started using this kind of a mixing to satisfy what are known as the Kohn-Sham exchange correlation energy density and the associated potential must satisfy certain fundamental properties. There are more than 17, 18 such properties which the unknown functional must satisfy if that is ever found, because of our knowledge of these interactions at the fundamental level. And there are two of them which I will cover in this lecture. One is, actually three. One is the self-interaction error, which I have alluded to before. Number two is the self-interaction is one. Second one is the exchange correlation hole density sum rule. That is 17. His scan reaches one, satisfies 17 conditions. We are in touch with each other. Okay, yeah. No, 17. Scan, the most is 17. So there are 17 constants that scan, which is actually a some kind of, it is not the ultimate, but it satisfies those. Saurav is smiling. Okay, so anyway, so the point to note is that I will just work out with just three basic conditions which the exact Kohn-Sham functional must satisfy. All right, and if it doesn't satisfy, you have to do something and be alert that no, this cannot pass. If it goes into the stream, your water will be polluted. So this is the important thing to note, right? So I will give some, but I'm trying to get hold of all the 17 things. Hopefully I will get it. If I get it, I will just share it. Now, so this is a local density recipe. The exchange correlation energy density in terms of the single particle or exchange correlation energy density per particle is assumed to be that of the homogeneous electron system, and you write this particular one electron multiplied by rho r and you integrate it, this is what you get. Now the next step is, of course, to write the exchange part and the correlation part separately. And as I have told you, the free electron homogeneous gas exchange part is already known at R in the small volume element. Okay, but correlation is nobody knows. Okay, you don't have analytic result for a correlation part, and therefore there have been a lot of simulation, and the early simulations were Vosko-Volk-Nusser and the Purdue 81 and 98. Purdue 81 and 98. I will talk about it. Okay. Yeah. So, all right. So, yeah. So therefore, this part is actually simulated. I will tell you how it is done. By the way, Vosko and Walter Kohn published a paper much before, about 10 years before, when Vosko did this particular simulation of the BISAG-N correlation piece. He had already collaborated earlier on, about 10 years before that paper. He had collaborated with Walter Kohn, and Vosko was in Toronto, University of Toronto, in Department of Physics. Okay. So this is the recipe. I will just rush through and not go through the details, but this was the first practical DFT calculation. What is important to note is that this piece that you have as you go up, they will all come to the limit of the lowest approximation to LDA. That's another important thing. Everything will just bump into LDA if you go on removing the improvements that you have imposed. Yeah, but I will tell you, scan is not very good. It's just a lot of hype, So let me just talk about it later on. So there are better functions that I think you will know in this workshop towards the end. Okay, so now what I'm going to do is this homogeneous electron gas. You separate exchange part and correlation part. Now this is something that the local density approximation is. What you do is you take a grid of the molecular density, which is totally unlike the free electron homogeneous gas of constant density. But you make that grid as small as possible so that this dV is a small part of the volume element, which is so small that smaller than that you cannot imagine. So local, just local at that point, smaller than that space you cannot imagine, right? In that space, you assume that the molecular electronic density for that small dV volume element around R is local density as given by the homogeneous electron gas of that density only in that volume. You go from one volume to the next, the density changes, but the approximation remains local. Right? So therefore, what you do is you put in this particular square at R1, then R2, then R3, you go on summing the integrand. This integrand is the same integrand over here, and then you sum. If you have smallest possible volume element, then that sum is the integral. Okay? That's the local density. And here the local density only depends upon, this exchange correlation energy density only depends upon the local density, which is the homogeneous electron gas. And you have to now put E of X and C. X is exactly known, but C is not known. You have to borrow very accurate results. For example, one of the things that Wasco Wilk-Nussbaum did was that there was a quantum Monte Carlo computations done for electron liquid. Like you have to have a background of the electron gas so that interactions are there between the electrons. And then the entire quantum Monte Carlo energy, which includes the correlation effect, is there. From there, you remove the exchange, which is exact for homogeneous gas, and the correlation is treated as a table of QMC correlation versus the density. Now you simulate this. Okay, how do you simulate it? Well, you use how best you can from your knowledge. And this is where there have been two streams, parallel streams of development of functions. That ladder I showed you, there are two separate streams that you can recognize. One is semi-empirical, parameterize, right? But parameterize have to be, parameterization can be from your ab initio understanding, or you should parameterize such that it reproduces some experimental results for a set of one or two molecules. The interesting and most distinct thing about the density function thing is that in principle, if you have an exchange correlation function which works for one system, and if it is good and if it is exact, it should work in principle for all the systems, right? That is guaranteed by the Hohenberg-Kohn theorem, right? But whether you will be able to have that accuracy or not, it's a different question. And this is why there are searches and searches and searches going on for last so many years after 65. Now, so therefore you sum this at R1, R2, R3. Remember, at each volume element, density changes. But inside that volume element, the approximation is that inside that volume element, the electron is behaving, density is behaving like homogeneous electron gas of constant density. Right? That's important to know. Now, therefore, although you say systematically you can't improve it, you can improve it. Why not? You have taken this as density, you put the variation non-local immediate vicinity of rho of R, R1, you go to dr1 and take the derivative, right? So those are the ones which are the gradient expansion. There are problems there which others will tell you, but it can be done. So now Manoj has told you all this about the Thomas Fermi part of the free electron gas in this morning. The energy, kinetic energy was this. This is the Fermi momentum defined in terms of Fermi wavelength. This is also defined in terms of the Fermi radius, which includes one electron inside the sphere of radius r. And kinetic energy of homogeneous electron gas in terms of the Wigner size radius was worked out long time back by Wigner, and therefore this was one of the starting points, so that anything that is very good or better than this in terms of the correlation energy density functional, the correlation piece, small epsilon c of rho, anything that is better than those good old result of Wigner, at the smallest level of approximation, it should be, I mean, at the lowest level of approximation, it should fall to the Wigner size radius and the Wigner correlation. So this is what this is. So therefore, XLDA exchange is this, and correlation becomes the Wigner one. So what was done was the quantum electron gas area that was simulated was for low density, intermediate density, high density, which is inverse in terms of the Wigner cell, because density goes in the opposite sense. So this is how it was simulated, and this was Wigner estimated that his results will be correct. You know, this is long time back in 1938. So Wigner correlation is still very good. It just does the computations without, before you submit it, the results are already out. It's so simple. I mean, those of us who have done this Wigner correlation in addition to the exchange, EX plus EC, it is still very good. Manoj is here, he has used this for very effectively, he has used for this kind of results. Anyway, so this is the Wigner EC. It depends upon RS. RS is nothing but, it's a measure of inverse density. And so LDA correlation in terms of Wigner correlation is this. This constant comes for a certain constant that has to be at r is equal to 0, it should give a number. No, this is potential. Potential. Dirac is, of course, that, yeah, it is yeah, it is Dirac, yeah. So at that time in 38, this is what was known. Okay, right. The other exchange came after Slater. It is 1951. Yeah, this is 1938. Pratim, this is 1938. Yeah. The other exchange came in 1951. Okay, right. Now, so these are the people who actually did the EC part. A very nice paper of, as well, everybody was quoting about this. All right. Okay, right. So yeah, here it is separately. Okay. So total energy available. So how do they do this? How did Wasco? Just to know how things are done. Okay, although we can now use it because somebody has already done it for us. We can just say VWN and submit and you will get the number. Okay, but what is it? So this is what it is. Correlation energy, no analytic derivation of this functional has proven possible as of now. Quantum Monte Carlo results of Seperle order of 1980 computed the total energy for fully interacting uniform gases in various densities. Different densities, different thing. Correlation is there. Then subtract the analytical exchange part, get the correlation part, right? Then you fit, then you simulate. Okay, and Wasco Nisar did that in 1980, design one, and there are papers by Purdue and co-workers in 81 and 92 which also did this. Again, as I was saying, one was a parameterization using some kind of a standard set of more accurate results. Other is giving the form of the functional purely basis on the ab initio solid state theory. And John Purdue has been propagating that for last almost 40-45 years. And the other part of the semi-empirical part has been propagated by and has been developed extensively by Excel Becquet, B-E-C-K-E, Excel Becquet, okay, Becquet function. So when I was in New Orleans, Purdue would show me, here is another Becquet paper. Physical review, one used to get for referring the other. And I was very amused. I mean, it's an amazing feeling that, you see those papers which are the Becquet 88 and so on. You see that. No. Yeah, he only gives number. Biggest, because he, yeah. So the thing is that you don't know it. So what do? You just try out. Anyway, so this is what was done, and then local density correlation fitting various things. Details are there. So this is his fit. So you can see this is a correlation part. RS is the basic homogeneous electron gas parameter, which goes as the inverse of rho, and then you have X, A, B, C, X, capital A, B, C, X0, and all the other things are defined in terms of X, B, C. So everything else is just known if you know these 4 parameters. This is Wasco, Wilk, Nussar become very popular. Almost everybody was using. And since Wasco came from, he had some Nordic background, and therefore Hedin Lindquist from Uppsala and all this Halstead group started using this kind of approach, and it was very popular. Because it was not, you did not know, no exact analytic formula exists. So anything that is giving you some numbers which are reliable and not absurd experimental is good enough. So this is what it was going like that. All right, the correlation energy with density. So yeah, now we have set the LDA. We know how to handle at LDA only density dependence of capital EXE in terms of EXE epsilon per particle, which can be integrated with density, and you can get the recipe, right? Local density approximation. And simply it only assumes that in the smallest volume element at any point R, at that density, you can compute, assuming that the electrons in that molecule is behaving like homogeneous electron gas. Right? That is LDA. Right? Now, there are, as I said, that there are many people who want to understand why this is working. Why it is not giving us absurd results like Thomas Fermi result that no molecules are existing in the Thomas Fermi model. Why? They also use the free electron gas approximation, but of course they did it for kinetic energy, which was a very large amount of energy. But here, so this is what it is. So this derivative of density over density, if it is much less than the Kf, which is given by this, as Manoj told this morning, this is the condition. That means that over the Fermi wavelength, okay, the changes are very small in the density, in that small volume element. That is one condition. There are other conditions here. I will not go through this. You can pick it up from the literature. By the way, these days, you have an advantage. You ask this question, define the condition for slowly varying density in LD, where LDA works. You will get 2 pages, 3 pages in Perplexity or ChatGPT or Gemini and so on. Use it. Highly recommended. I tell all my students to use anything that they can search using the AI, and you will get, of course, you have to verify it. At the end, it will return that the smart machine, the AI ML things may not be exactly 100% exact. You have to check it out. But that is, of course, there all the time. So far, so good. We are still important, not the machines. Anyway, so this is the recipe that we are working with in the exchange correlation potential. Now I will go to the 3 parts, and those 3 parts are, let me go to the 3 parts that I am considering here. The exact properties that are a constant, the exact constant that true exchange correlation energy density function must satisfy. There are many, but I am choosing 3 of them because they are conceptually very important in chemistry. Okay, and that is electron-electron interaction must be self-interaction free. Okay, the density is there. It has the density contribution from every electron. Now, if you are using that as the key parameter to decide all properties, there will be caution that you have to correct for that. So electron-electron repulsion in Hartree-Fock model is very nicely corrected. The exchange part and the Coulomb part at I is equal to j cancels out. When both electrons phi I and phi j are the same, self-interaction cancels out exactly from Coulomb part and the exchange part. Exchange part is minus, Coulomb part is plus. Right? Exchange is stabilizing interaction. It corrects for the extra interaction in Coulomb that you assume because of the average density. Right? Now, second thing is, there is a requirement of the exchange correlation hole density. I will not go through the derivations, but I think Pratim touched upon that, the two particle probability. But simple thing is as follows. You have an electron distribution and you have a reference electron which has a charge and it has a spin, right? And what is the correlation? Dynamic, as everything is moving, this reference electron is moving at all r, it will go around everywhere, but it will obey the physical requirement of quantum conditions that two spins of the same type, that this reference electron cannot allow any other n-1 electron in which the spin is the same to come on top of it. It will avoid it. So that is a correlated motion due to the spin. And the other one is, of course, the obvious same like charge. Minus electron charge, minus electron. They will never be on top because of the Coulomb repulsion. Right? So therefore, at any point, suppose it is avoiding the other charges. When this electron is integrated out over the entire space, its total normalization will be 1 because electron is 1. It is distributed all over the space. Reference electron is all over the space. So its density, small, but total electron, 1 electron density will be 1. So it can only avoid the total other electron densities. That means some kind of a hole will be created around this electron, which will not allow the like charge as well as like spin to be around nearest to it. It will avoid, right? The total avoidance will be equal to what is avoiding the other electrons. So total exchange correlation hole density must be equal to -1, right? Avoidance, that this electron is moving in the field of dynamic motion of all the n-1 electrons simultaneously, correlated motion, will avoid a total integrated charge, correct for, with minus sign, exchange correlation hole, that must be subtracted from the classical Coulomb interaction, right? So therefore, this part of the hole must integrate to -1. So exchange correlation rho hole density integral over the entire space must be -1, right? Now, we know that this hole density x rho xc hole at R1, R2, this hole will be separated into rho of x and rho of c. Now, what about rho of x? The important thing is that rho of x is itself such that like spin cannot be near each other, cannot be on top of each other. It will always avoid, and therefore one like spin will avoid the like other spin of n-1 electron equivalent to its total density, that is 1. Reference electron all over the space is 1. It will avoid like spin as 1. So therefore, the exchange hole density itself is -1. Integrate exchange hole density over the entire space, it is -1. Integrate the exchange correlation hole density over entire space, it is -1. What it means is something very, very strange, because this is the way that we have partitioned the exchange correlation effect. It says that the EC hole density integrated over entire dynamic motion of n-1 electron as reference electron is moving everywhere is 0. Not to say that it is not finite at the instantaneous location of R1 and R2, but if you integrate it, it is 0. Now this is very difficult to probe. And that is why the post-Hartree-Fock methods are very, very difficult. They converge so slowly that you get frustrated. I don't know. Yeah, but that is.
But if they are coming with the same spin, MS is also same.
Yeah,
so
yeah. So I did not go through the details, but I'm just giving you a conceptual thing. You know, we one electron over the entire n-1 electron will avoid one electron because your total field has to be due to n-1, right? But like spin itself is 1. So therefore, the charge, the Coulomb correlation must integrate to 0. Not that at R1 and R2, the value of the hole is finite. So what is the consequence? I am not going through the equations. I will show. I just flash the equations later on. Ex is always negative hole. EC can be negative and positive so that it integrates to 0. But what is positive and what is negative will depend upon R1 and R2 between the like charges. And that's the post-Hartree-Fock Coulomb interaction, Coulomb correlation. That is difficult. That is why you need something which is giving you way out of that. And this is where the DFT is actually becoming popular. And last one, I put the wrong one. Last one is derivative discontinuity. It's very important, but we can understand this because it's very easy to understand at our level, right? And also talk about it. So these are the 3 basic things. Incidentally, there are only a few functionals which can be counted on fingers which satisfy the last condition. Okay, and I'll come back to what he was talking about, that TC being mixed with the XC. People are now using that to impose the derivative discontinuity. There's only one functional that has come up in 1924. Okay, but anyway, let us first understand what are these conditions, right? So I will go through very quickly, not in detail, Hartree-Fock exchange, okay, which is the exchange correction due to the like spins with minus sign, which takes out the extra Coulomb, rho 1 and rho 2 interaction in the Hartree term, right? It does not forbid the like spins in the Hartree term. So exchange part has to remove the density from that interaction. So let me go back. So 1, 2, 3, 4, 5. I quickly do this because you can always pick it up from everything is very well explicitly recorded here. So let's consider the Hartree-Fock orbital equations. The Coulomb potential is this. Okay, this is the potential due to n-1 electrons working on a reference electron occupying the orbital chi-i. It is spin and space, and this is the multiplicative potential. Coulomb potential is multiplicative, and that is the Hartree potential. That is a classical thing. Classical, okay? Classical part. Rho 1, rho 2. Now, the Hartree equations, we have also, this is the J part, and I must start with here. So this is the J part here, right? This, the reference electron. So you have effective Fock operator, the reference orbital energy, and the Fock orbital back. So this is an effective potential, very different from the effective Kohn potential, effective Kohn-Sham potential. Okay, it is non-local. Right? Now, how does it look? F1 is the 1 electron term and the 2 electron term, which is the Coulomb term. This is other rho, and this is the reference electron. And now you see the exchange, what it does. The extra sum over all J, which includes I, self-interaction, is now corrected for, in addition to the other antisymmetric requirement that if you exchange R1 and 2, the wave function should be antisymmetric. That leads to this quantum effect, but only at the like spin type. Okay, right? Not the like charge correlation, like spin correlation, Fermi correlation. Now this is minor, so it subtracts. The extra repulsion that has been taken care here is removed when I is equal to J, but its structure is different from this. It is not the simple charge, not the square of the chi J. It is chi J, chi I, quantum. There is an interference. There is a wave nature playing here. This is purely quantum, okay? And it has with minus sign, and you see it switches the I outside with J. And therefore, the potential becomes, if you are solving for chi I, it depends upon chi I itself. So for if you have lithium 1s and 2s orbital, for 1s orbital the exchange potential will be different from 2s orbital at the same point, right? So this is non-local. Now, what we do is, to analyze this, we say that, okay, let this be the Coulomb charge, square of the density divided by R12, Q by R12. So this is the Coulomb charge divided by R12. Similarly, the exchange charge will be this one, Ji of the 2, and divided by 2 will be the potential, but the exchange charge. So you are giving the same footing to so-called the exchange charge density, which is quantum, but you cannot, this is not a thing that you can measure as charge, right? Now, this is Coulomb, this is multiplicative, you multiply by this, you get the operator same, and this is back. And that is local, but K part, that exchange part, which is having a minus sign, which corrects for the extra charge in that. Remember, a very important point to note, which has been pointed out, I think, by both speakers this morning in the pre-lunch session, that if I is equal to J, when I is equal to J, the self-interaction exactly cancels out from Coulomb and exchange, right? Now, let me warn right here that if you are changing the exchange potential, the exchange correlation part, if you are putting the free electron gas, then you are not correcting exactly. You are putting rho to the power 1/3. There is nothing like I is equal to J exactly. Partially maybe, but exactly it is not. Okay. So therefore, there will be some self-interaction correction to be done, or some self-interaction error that will be left in the LDA. That is point number 1 to note. Okay, because we are not doing it exactly. You are replacing it by a local exchange. Okay, so therefore, at I is equal to J, nothing like full correction. There will be partial correction. All right, so that is point number 1 to know. So that is why that has to be implemented, and that is what many of us did. And Purdue is well known with Zunger to do the SICS, LSD. Anyway, so this is one part. Mermin, yeah. By the way, both Mermin and Hohenberg were the same good student in Harvard. Mermin was with Schwinger and he was with, as I told you, with Martin. Anyway, so now this was the problem of Slater, who took it up. He said that Hartree-Fock, because of a non-local property of the exchange, cannot be done for solids. There are too many electrons, too much of computation required. So he is quoted as saying that you have to decide. Slater said it in 1951, if you read the literature. Do you want to do exact computation or you want to do approximate computation which is reliable? That was set forth by Slater. And his free electron gas approximation, which led to X-alpha theory, is actually just the precursor after Thomas Fermi model of the Kohn-Sham exchange potential, except by a factor of 2/3. Yeah, he was here. That's why I was coming to that. And Professor Gopinathan did pioneering work in correcting for that self-interaction by modeling the correlation exchange hole. If you read his papers, he and Whitehead, Tony Whitehead in Montreal, both of them together did that. And then, of course, based on a large citation of that, he was directly appointed as associate professor here. Anyway, so that's nice. Anyway, so this is good. So I will not go through quickly. You can just, so he tried to average this so that that non-locality is gone. So what he did was, he averaged the exchange part for each orbital, which is different. He took the sum and divided by the total number of orbital and obtained the average exchange potential. So that is what changed the non-local thing to local. The problem was that he started with the variationally determined Hartree-Fock equations and put the free electron gas approximation to compute the average exchange potential. The smartness of Kohn was that he started by free electron gas exchange potential and minimized it. You remember that Euler-Lagrange equation? The difference was a factor of 2/3. Everything was the same, a factor of 2/3. Anyway, so that is again very interesting part. And but Walter Kohn did much more than that. And finally, the whole concept is here. I will not go through that. Essentially what happens is that this correction exchange charge at this point becomes exactly equal to the charge of the like spin at that point. So that the same spin cannot be on top of each other. But that correction hole decays so fast within the smallest volume element that immediate vicinity of this electron, all the other electrons can contribute, including the same spin. Right? You can't have this, no two electrons can have all the 4 quantum numbers the same, right? But separate them by infinite energy distance? Yes, they can have. So this is what that hole is about. So this is correcting. So therefore, this is the density that electron is carrying of the spin of the same type of the n-1 electrons. And this is then the representation that if you consider the homogeneous electron density in just around the vicinity of R, then that is the free electron gas approximation. So this is something that is worked out. Now let me go through the electron-electron interaction must be self-interaction free. So that is there. Now we come to the exchange correlation hole, which I have already talked about. Essentially, the exchange hole is this, which is -1. The correlation hole is this, which is 0, and the EXC hole must integrate to -1. So an important consequence is that only spherical average of the exchange correlation hole can attribute to the exchange correlation energy. So this is the integral. But then let me come to after giving you that requirement that the exchange hole must integrate to -1. Correlation hole, though integrand can be finite, but the total sum, it can be positive and negative. Exchange hole will be always negative, correcting. And the correlation hole can be positive and negative, depending, but the sum total is 0. That is important. And that's difficult to compute. And the last point is the energy as a function of particle number. Right? Please pay attention to this because this is still an open problem. The plot of energy of an n-electron system as you change n from one integer to another integer, right? So if you have sodium, you go from sodium plus to sodium neutral to sodium minus, and it's changing from 10 to 11 to 12. Okay, so this is what is plotted here. N1, N0, N1, N2. Okay, 3 successive, right? And you plot the energy. Then what turns out is that it is a piecewise linear function. There is a slope change at the integral value of n, right? The slope change and the integral value of n. Now, as I have told you, almost no existing functional satisfies this. They are smooth because of the density dependence, which can be varied in fractional numbers, and they will go smoothly. I will show you some pictures. Okay. Yeah. Okay. So, well, so that there is a derivative discontinuity which is missing from the approximate functionals that people are developing without paying specific attention to this particular constraint. It's very difficult to follow. But then let me tell you that the same functional at n plus delta and n minus delta. So left slope and the right slope at n is finite, greater than 0. What I'm indicating is here. The slope here is finite. The slope here is finite. And the difference is finite. That's derivative discontinuity. Now, this is finite. One can prove it in many. By the way, I have got so many of the slides from my time from 1977 onwards that I don't remove them because some of them are handwritten by people like Purdue and so on. So you will see some of them. This is from Trigway. So this is a famous Purdue quote. Where am I? Oh, I pressed the wrong button. Okay, I'm going there. How much time do you have, sir? 5 minutes? Oh, 15 minutes. Oh, good. Yeah. Okay. All right. I not talked about the individual performance of that. I will tell you about this in general, about the LDA. Performance of LDA. Okay. General performance of LDA over the years. Okay. One of the things is that for molecules, LDA overbinds. It overbinds. The energy is given more stable than before. That is because of the self-interaction problem. Okay, but it gives reasonable structure. The geometry is very good. Okay, better than Hartree-Fock. Right, this is what Kohn always quoted. Are they not better than Hartree-Fock orbitals? Okay, so that's the reason. Kohn-Sham orbitals are better. Now, this is the John Purdue handwritten thing. This is how the Purdue-Wong correlation piece was parameterized in the LDA. So what he did was that at high density limit and the low density limit from the solid state theoretical analysis of the solid metals, he was able to get the expression on the right hand side. It is not very clear. There is a RS dependence of all the terms, and A, B, and are constant, and order of the approximation is given in terms of RS. So this is for the high density limit and the low density limit. As I told you, that correlation piece is only known computationally at a given set of densities. So you have low density, intermediate density, and high density. So intermediate density, lot of results are there on Separelli-Alder. Low and high density, he used the ab initio methods to simulate those results. So that was Purdue, Wong, EC in LDA. He did it twice. One was in 81, another was in 92. And they are, the 92 one is obviously much better than before. And so this is a 92 paper. So this particular parameters are different. B1, B2, B3, they're all parameters. And they give you the Wigner correlation piece in the limit of no RS. Now, why does LDA work? So this is important for us to know, because chemists are about, they want to have a particular data set of, let's say, 200 or 300 experimental numbers, let's say reaction barriers or geometries, bond distances, bond angles, of a collection of molecules which have different bonding characteristics, so that you can test the LDA results whether for all bonding situation LDA is reliable or not. Okay, so including hydrogen bonding. Remember, if you do an exact calculation, for example, has been done by the Polish group, Pachuki, Rychelski, and all these people, Silverowski. These are the people who have done extreme computation of James Coolidge type of functions, which explicitly include R12 in the wave function theory, something like hundreds or 300, 500 expansions. And H2 molecule is known to up to 15, 16 decimals in energy at all internuclear distances. It predicts the united atom and the separated atom correctly. That means all interactions, including dispersion corrections, van der Waals, and everything is there. Right? If you do exact result, but that's unfortunately not possible. In fact, it is not possible even for hydrogen molecule. What you know is that you can do it almost near exact. Go on doing more and more terms, go on, but all those orbital concepts and everything are no more there. It's R12, just the numbers now. Okay. So now, why does LDA work? Let's take a look at it. So accuracy of LDA. This is a general result. There are almost every month you will find there are 2 tests of the functional. Some new functional comes, some other group uses that functional because it is already embedded in the code, and you have a particular data set, and you say, all right, let me see whether this new functional behaves well for, let's say, reaction barriers or not for 300 experimental results. Okay, and then you say, oh, this is on the average, mean average error is about 0.2 atomic units, so it is better than the previous function, that kind of thing. So this is what is going on. Now, geometry of the molecules and bulks, these are all solid state molecules, solid state systems. So about 1 to 5% error. Cohesive energy is in this range of electron volt. Dipole moment error is 2. In spite of the crude approximation, it is a wonder that dipole moment, which is dependent so much on the charge separation, and is so non-local in effect. Okay, you have this kind of accuracy on the average. Thousands and thousands of molecule results are available, right? And excitation energy, it underestimates the excitation energy. That is because of the self-interaction error. And the van der Waals energies, not at all tolerable. It is very bad. If you want to do dispersion correction, and here this is not at all good. Now deficiency, what are the deficiencies? No, these are general. I will try to explain some of them, not all, but some of them, which you can pick up from the literature. What are the problems? The band gap of solids is underestimated by almost 50% band gap. This is because of the non-satisfaction of derivative discontinuity. The delta xc is not there. Left and right slope differences is not there. It is continuous curve. Right? It's not there. So therefore, it underestimates the band gap. But bandwidth, which has to do with the lifetime of the state, it overestimates. That is because of self-interaction error. Self-interaction error is not cancelled out. Therefore, the repulsion extra is remaining in the Coulomb part. And therefore, the repulsion makes the density go outward diffuse. And therefore, the hopping overlap from point A to point B on the sides is more, right? So one is underestimation of the band gap of energy, and the other is overestimation of the width, bandwidth. They're two different things, okay? It's important to know. Then, of course, this we know, van der Waals interaction. Most of the Grimme had to do the dispersion correction separately, D1, D2, D3, as you know, and of course there are many others which are really popular one. And lattice constant underestimated by 50%, not bad for solids, because at certain times you could not do anything. No computations could be done because only Hartree-Fock was known. Then poor description of 3D metal. 3D metals, especially the spin properties, are very bad in LDA. All right. Then the activation barrier of chemical reaction is largely underestimated, again because of the self-interaction error. I will explain this. Then, of course, for metal oxides, the orbital, it's all spin effects, they are not very good. Okay, because the homogeneous thing is not taking care of the unlike spin polarization. All right, this we already discussed. Yeah, one of the saving grace of the LDA is that we always take the difference of energy. Two LDA calculation has to be done. A going to B, you compute LDA of A property, B, and take the difference. There is a cancellation in the delta SCF method using LDA. Okay, that helps, right? But there is something more. Some rule of exchange hole density. It is very interesting to note that the only way that such a crude approximation is able to give you geometry so good, better than Hartree-Fock, is because it satisfies the exchange hole, XC hole density as -1. Individually, exchange and correlation piece hole densities may not be -1 and 0, but together as you integrate, it is -1. That is because you are using homogeneous electron gas, right? So this is the saving grace. This is very important. It is a requirement that is not followed by simple GEA, gradient expansion approximation. After second derivative, it starts to give you positive correction due to exchange, and the correlation becomes like very, very oscillating. So Purdue and others, when they took the expansion of gradient expansion, so not just rho, first derivative, second derivative, you go through the Taylor series. He had to cut off that to get you the GGA, so that wherever that particular negative characteristic of the exchange hole is not followed, he just by hand implements it after cutting off from there. Maybe Manoj will talk about it later on. So this is one. So, but the sum rule of exchange hole density is obeyed. And well, I have given all these things together here. This is the last part, which is now I'm going to talk about in some detail and close the talk. And this has to do with the self-interaction error. So if you have one electron system, you have an LDA functional. It should work for all electrons. For one electron system, there has to be an exact cancellation between the E Coulomb and E exchange, because there is no self-interaction. There is only one electron. Right? So therefore, this condition, finally LD has a big drawback, which is that it does not satisfy the one electron limit. In one electron limit, if you take any functional, any approximate functional, in the hydrogen electron, one electron limit, there should not be two electron situations hanging around. All right. You should have this result that E exchange must be exactly equal to the opposite of Hartree part. Totally cancellation, right? Because the two electron part is not there. 1 over R12 for Hartree must exactly cancel by 1 over R12 in exchange. If you have one electron, right? So all functional must go to the one electron limit, right? So this is, therefore, EC is 0. Right? Because if this becomes it, then EC is 0, and then leaving just the contribution from the nuclear electron attraction term in this, that we know. Hydrogen atom, what it has nuclear electron attraction. There is no other interaction. Right? So all, in one electron limit, all functions must solve, because that is a limit. Right? Now, let's see what happens. So this is the picture I liked very much. And so do the students that I have been interacting with. That is, En versus N, the exact result is a dotted one. There is a derivative discontinuity. And the Hartree-Fock result is the green one. Okay? It mildly satisfies the derivative discontinuity. But all DFS, all density function of all, except 1 or 2 out of 400 and 500 that we know today. Okay? Right? That is like this blue curve. No derivative discontinuity. No derivative discontinuity. Therefore, the band gaps are totally offset. All right, and it is underestimated. So therefore, let me just give you the result why it is. So the fundamental band gap is given by Kohn-Sham HOMO-LUMO gap plus the derivative discontinuity. This is 0 for LDA. Right? So where delta is the derivative discontinuity, LDS problem, LDA lacks delta C entirely. It is smooth. There is no derivative discontinuity. Left and right, same. At a point, left and right derivatives are the same. Right? So therefore, this derivative discontinuity is missing, and the cause of systematic underestimation of band gap. Then, I think I am going to finish now. And the SIA limit, the self-interaction error enhances the band dispersion, makes the bands wider. The band width becomes fatter, thicker. Because self-interaction error is there is extra repulsion, electrons are moving around in the outer space, which they should not. They are not supposed to be doing that. Okay, and therefore the overlap and the hopping overlap interaction is also increased, and this is the reason for the opposite way of overestimating the band width as opposed to the underestimating the band gap. One is the energy, other is the distribution of the density. So this is important to know. And well, the same thing that I said, unphysical X repulsive potential remains. The erroneous self-interaction, which should have not been there, remains, because the exchange part which cancels is exactly for I is equal to J is no more doing the same job, because you are replaced it by free electron gas exchange, and it pushes the densities away from being localized. So this is also known as a delocalization error. These are the technical terms which you will come across when you read the literature. Right? So SIA error leads to the delocalization or the dispersion effect in the density. And well, I have given here what happens if you have the localized electrons, wave functions are confined near atoms, small overlap, small hopping integral. This is about the band width. And if you have delocalized electron, you have large bandwidth, opposite is true. And the bandwidth scales as 2Z. Z is the number of coordination number around the center in the solid, and 2ZT is therefore the hopping parameter T, which depends upon the dispersion being larger, so becomes large, and therefore this particular width becomes large. So self-interaction error increases the T because delocalized orbitals have greater spatial extent and overlap. So point-to-point overlap, it becomes larger. Hopping. All right. So this is the band. This is the dynamic bandwidth effect. So the energy, how much is the lifetime of the energy? How long it is sustainable? Right. So this is what is happening, and Well, there are many other things, but I will close it here because I have come to end of my talk. One could go on and on, but I will share one article that I told Somen this morning. It's a memoir volume on Pierre Hohenberg. You will get a glimpse of how many of the top people of that era actually knew him and had a lot of respect for him intellectually. So it's worth reading. Of course, Ramamurthy Shankar is one of them. Right? J.W. Willard Gibbs professor in Yale. Gibbs came from Yale, the Gibbs-free energy. Gibbs. Okay, so I'm done. Questions are welcome. Why students are not asking? Am I not making myself clear? I hope there's something. Please ask any question if you have.
Hi, sir. So nice talk.
Thank
so
you.
my question is that I understood the source of the self-interaction here because the exchange correlation kernel is not exactly cancelling the Hartree kernel. So we are getting the self-interaction, but
that's only for the exchange part.
Right. So if I include a hybrid functionals, so a portion of Hartree-Fock exchange will improve it. So my question is that what is the source of this derivative discontinuity error? That is not very clear to me.
Source of derivative discontinuity is that the density is piecewise linear. If you want, I can explain to you. Bob Parr did it explicitly in a mathematically rigorous manner. So sit down. One of us is standing is enough. So it goes like this. So there is something, I have to borrow the fundamentals of information theory here. Okay. And there is a very nice information measure between the two probability densities. It's a rigorous information theoretical measure in all mathematical sense. It's called the deviation. No, it is. I'll tell you what it is. It is called Kullback-Leibler dispersion or distance. So it goes like that. If you have a probability rho 1 and you have another probability rho 2, information wise, how does the two probability distributions differ from each other in the form of information that the density contains? Now this information is statistical information. So it goes as integral, and the integrand is rho 1 log of rho 2 divided by rho 1. Now rho 1 is called the reference density, reference probability. Okay, this is a measure. So the integrand, it goes as log ratio of rho 2 to rho 1, and it gives you oscillations telling at which points rho 2 is different from rho 1. Okay, and if you integrate, you will get a number. That's a measure of the difference. So Parr, yeah, of course, there are many things, but the simplest one that connects right now to your question is the following: that if you take the reference density rho 1 as 1 or constant, okay, then this particular prior density becomes 1. So everything becomes log rho. Now it is reference. How is it different from constant density distribution? So if you have a constant density probability, how is it differing from the constant probability in terms of the Kullback-Leibler? Now that particular plot is piecewise linear. If you plot log of any atomic density versus R, okay, it will be at the shell structures, it has a derivative discontinuity, right? Now this is in a way reflected in terms of the independence of the energy, but not in the specific values of approximate function. In terms of simple-minded experimental evidence we have. One is remove the electron, ionization energy, experiment. Put the electron affinity, experiment. So N is changing physically, effectively in the experimental measurements by 1. Now it is here that on left and right of any n, the derivative is discontinuous. Otherwise, there will not be energy required to remove an electron and energy required to push the electron, right? This was already given by Mulliken also indirectly as Mulliken electronegativity. Yeah, is it clear?
Any other question?
Yeah, Soman. Soman.
So, you mentioned one thing about that DFT orbitals being better than Hartree-Fock.
LDA.
LD. So, but what do you think about this? I think it's old. It was there before, but now a few groups are popularizing it. Is using Hartree-Fock density for DFT.
Yeah.
What do you think about that idea?
See, this is very nice fundamental uh, background, and that is the adiabatic connection model. Okay, so what you do is you take the exchange correlation thing and connect it adiabatically from rho lambda is equal to 0 to lambda is equal to 1, keeping the density at each lambda the same, right? I can explain to you, I have a very nice presentation on that. So what happens is that at lambda is equal to 0 and lambda is equal to 1, suppose the curve is like this of the integrand, okay, lambda is equal to 0, lambda is equal to 1. At the two limits, at the two endpoints, one corresponds to the Hartree-Fock level at lambda is equal to 0, and the other endpoint, it corresponds to the fully interacting unknown functional. So what they do is, and this is the basis of hybrid functionals. So supposing, it is like this. So the curve goes like this. This is the Hartree-Fock piece. Lambda is equal to 0, lambda is equal to 1. Here, lambda going like this, and this is the integrand of the adiabatic. This is the integrand of the adiabatic connection formalism. At each lambda, the density remains the same, adiabatic. Okay, we already used it for two extreme in Kohn-Sham model. Now here at all lambda. Okay, now this part is Hartree-Fock. Right. What Baker did was, he said that, oh, the long range behavior is exponential in most of this LDA and GGA. It decays. It doesn't decay as -1 by R because of this error. It goes as exponential, right? Exponential decay. So to correct for that, what he did was that let's mix a part of Hartree-Fock, which is guaranteed to give you -1 by R dependence. Okay. But there is a catch which has to be understood now. So I make it the point. So now what he did was, all right, he said that, well, if you, so our aim is to get this area, this particular curve. This area is what we have to get. The area under that integral, right? So this will be this plus this much. That will be this plus Hartree-Fock added and whatever is added. Suppose he assumed that this is a straight diagonal, right? So the density functional part, the exchange correlation part will be half and the Hartree-Fock will be half. That is behind half and half Baker hybrid functional. Right? Now everybody started parameterizing 1 and 1 minus alpha. 1 minus alpha is Hartree-Fock part. Right? Went on for several years. Single hybrid, double hybrid, hybrid in exchange, hybrid in correlation, all kinds of, because once you know that idea is idea, everybody can use it. Nobody has copyright. Now, the point is that it does not decay as -1 by R. Right? So, what is your hybrid functional? EXC hybrid or double hybrid? Double hybrid has to do with correlation also. Hybrid functional of density. Okay, it will be a certain Hartree-Fock exchange plus correlation part, whatever it is, whether you want to single hybrid or double hybrid. But Hartree-Fock exchange is there of 1 minus alpha, and let's say LDA is there LDA X of rho alpha or lambda. Let's say lambda. Lambda is better. Okay. Now this lambda is parameterized. But you see the problem. The Hartree-Fock part does not go as 1. It goes as 1 minus lambda by R. You get this point?
Yeah.
So therefore, the tail correction is bad.
No. It will only be 1 over R when you get 100% Hartree-Fock.
Yeah. So what is done? Range separated.
Yes.
Right? That's the idea. It came in it came in 30 years after 64. There was a meeting in Krakow, which I attended. Walter Kohn, everybody who was active at that time was there. And that was the idea. It started with our Paris guy, Andrea Savin.
Yes.
Savin's idea.
Of course.
Okay. So you do, you range separated. So everywhere the interaction is 1 by R12. This is the interaction, right? 1 by R12, right? And you have always this, but once it will be added in one region like this, and then there will be a blending part of the range, and then there will be another part of the range. Every time at the long range, it will go as minus 1 by R1. That's the power of range separation idea. There is one paper, one author, one speaker is speaking on range separation for excited state.
Yes.
That's very novel. It works very well in the ground state, but excited state also it works well.
Yeah.
And there are many, many ideas that chemists can actually contribute here. One of the ideas is the shell structure. Okay. Right, fine. You got the idea, right?
Yes.
Oh, welcome. Pleasure. Thank you very much.